So now we're going to talk about magnetic forces on a current carrying wire. So we use the right hand rule to find the direction, and we'll use the lib formula to calculate the force. So as we know about electromagnetic forces, acting on a distance, you will only get a force if you have something moving in a magnetic field, a charge or a current. Current is the movement of charges anyway. Perpendicular, so you will use the right hand rule as we did from before. So instead of the V that we had before, which was the charge that was moving, now we have the current. The current is the thumb. Everything else is the same. B and F are the exact same fingers. B is there, F is there. To find the direction of the magnetic force in each wire, you can go ahead and solve it. And let's use handy again. If I was to quickly do this, I've done so many of these examples with you, but I'll do just a couple here. So if I was to take my current and I'm pointing it into the page, B is going to the right. If I do my hand like this, you will see that my force is pointing down. If I had my current coming out of the page, remember the dot means out, so I'll have my hand over here, I'll point it out, and I will take my B and point it up, and you can see what is happening is if I hold my hand like this, you can try it yourself, the force is pointing to the left. Okay, so if we have current flowing through a wire in a magnetic field, we need to know, of course, the current. We need to know how long the wire is, which is inside this field of ours. And of course, we need to know the strength of the field itself. And the direction will also make a difference. If there is an angle, the force will not be 100%. It will be slightly different. So that's why we use the lib sine theta. Length, current, magnetic field times sine of the angle. That will help you find the force. Be comfortable with rearranging this as well. You might need to find B, you might need to find L or I. For that, you just take these to the other side and it becomes divide. If I wanted B, F divided by Li. Okay, same idea if you wanted L, F divided by IB. And the sine theta, bring that across as well. Why not? Okay, so to find the magnitude and direction of the force, well, we can find the magnitude of the force, nice and easy. Lib sine theta. We have the length, 10 centimeters, which means 0.1 meters. We cannot use centi, we have to use meters. Multiplied by the current, which is 12, multiplied by B, 0.5, times by, in this case, sine 90, you will get 0.6. If you find the direction of it, you can point your your index finger to the right, you take your thumb, point it down, and you will have your middle finger pointing towards you. The force will be coming towards you, which is out of the page. If they're parallel, nothing. No angle, no force. And if you have an angle, same rule as before, but instead of sine 90, we will use sine 30, and you will realize that is half, 0.3, and the force is in the same direction, out. You can apply this now to a loop of a current. If you put a loop of current in a magnetic field, you can see perhaps it may rotate. But looking over here, if I have my current pointing up, field pointing towards me, I have a force going to the right. And if I have my current pointing left and my field towards me, you can see the force is going up. So that's not really exciting because this force will just cancel with this, and this will cancel with this. That's nothing going on here. But on this one, things have changed. There is no force here and no force here, so these two will not move. But we do have a force on this one. We have a force on this one coming into the page, like this. If you check with your fingers, you take your I pointing it up, B pointing right, middle finger will point in. But when it's coming down, it's the opposite. The current is coming down this way, you will find that you have a force coming out. So this whole loop will actually rotate and it will spin around. And that is the starting of a working DC motor. That's how we can use it for. Okay. So applications of torque on a current loop. This is focused towards grade 12. So grade 10, you do not need to listen beyond this point. Thank you. So simple DC motor, as you know, because we have a magnet, we have a field, and we have a current flowing through the field this way, coming around, and this way. This has a force acting down, and this will have a force acting up, and they are helping each other. This whole loop will rotate around in circles. You attach it to a battery, which will supply the current, of course, and that will create this movement. Turns it into mechanical energy. It will just spin around. Very, very nice. if you were to calculate the torque for this, you can do. We know the torque from before is force times radius, or force times distance. There's two forces that are helping each other out, so there'll be two of them. And you can go ahead and derive the formula for torque, which we do not need to know. We can just directly go straight to the final formula, which will just be Bian sine theta, or Niab sine theta, however you want to say it. NIAB sine theta. Let me make this on a... Do I have this on a bigger page? Yes, I have. There it is. Calculating the torque in a square coil, we can just do NIAB sine theta. Number of turns, which is like the number of loops around this. You'll see like a hairy arm will be looped. Number of turns multiplied by the current, area, magnetic field, sine of the angle. Torque is max when the surface is parallel to the field, because when the surface is parallel to the field, that means the fingers are actually perpendicular. This might be a bit confusing, but just remember the surface, which is this thing here, if this is parallel to the field like this is parallel. If I'm drawing a parallel, that means my current is flowing perpendicularly. This will be my perpendicular for the current here and here. So that is a badly drawn explanation. I will show you this again in class. Okay, to find the maximum torque on this example, well, we can just do sine 90, because that's when the maximum torque will be. So BIAN or NIAB, doesn't matter. You just multiply all the numbers out together, yeah? You multiply all the numbers and you'll get your answer, 3 Newton meters. That's the unit for torque. Thank you.